Okay, well, I welcome you all for this new session. In this session, we will derive the stiffness matrix for the beam element. In the last video, we have derived the Hermite shape function. These are the four shape functions. H1 is equal to 1 by 4, 2 times of 3 zeta plus zeta cube. It is in terms of natural coordinates. All the Hermite shape functions, it is in terms of natural coordinates. Okay, to derive this stiffness matrix, we already know that it is derived with the help of strain energy. What is strain energy? Strain energy equal to half of integration of sigma t epsilon into dv. Okay, half of sigma t epsilon dv means a into dx. Okay, we need to substitute what is sigma and epsilon for the beam element. Then substituting all the things, if you eliminate displacement values, that is qt and q, then the remaining what you will get, that is stiffness matrix. In this strain energy, you need to eliminate all the displacement values, that will be the stiffness matrix. Okay, in the same fashion we have derived the stiffness matrix for bar element and truss element. Okay, next let us see what is sigma and epsilon for the beam element. We know that bending equation m by I equal to sigma by y equal to E by R. Here m is moment, I is inertia, sigma is bending stress, y is distance of the fiber from the neutral axis, E is the Young's modulus, R is the radius of curvature, where R is equal to 1 by R is equal to dou square V by dou x square, where is the displacement. Okay, by these two terms we can write sigma as E by R into y. Okay, so we are substituting R value here, 1 by R value, it is dou square V by dou x square. So sigma is equal to E by dou square V by dou x square. Okay, we know that stress by strain is Young's modulus. So strain is equal to stress by Young's modulus. This is the stress equation. If it is divided by Young's modulus, then it will be strain. If it is divided by E, then we will get y is equal to dou square A by dou x square. This is strain. So stress is equal to E by dou square V by dou x square, and strain is y into dou square V by dou x square. Substituting this stress strain in this strain energy equation. We are substituting this stress and strain equation. See here, it is in terms of Cartesian coordinate. Okay, see here, stress and strain, stress is equal to y into dou square, strain is equal to y into dou square V by dou x square, and stress is E into y dou square V by dou x square. Okay, here stress and strain, it is in terms of displacement, dou square V by dou x square. Okay, what is V here? Displacement. Displacement, it is expressed as the Hermite shape functions and the nodal displacement. V is equal to HQ. V is equal to HQ. What is H? H1, H2, H3, H4, and Q are the four nodal displacements. So dou square V by dou x square, where V is equal to HQ, where H is H1, H2, H3, H4, and Q, it is the four nodal displacement. It is in terms of global coordinates. Now, as our H1, H2, H3, H4, it is derived in terms of natural coordinates. Let us bring this into dou square V by dou x square into as the natural coordinate. Okay, we know the relationship between the local coordinates and the natural coordinates. Dou v by dou zeta is equal to Le by 2 dou v by dou x. It is derived here. Dou v by dou zeta. Dou v by dou zeta is equal to dou v by dou x into Le by 2. Okay, dou v by dou zeta. So by this, dou v by dou x is equal to, it is written in terms of dou v by dou zeta. What is required here? We have dou square V by dou x square. What is the value of dou square V by dou x square? Now we need to write in terms of dou square V by dou zeta square. See here, dou V by dou x is 2 by LE dou V by dou zeta. Okay, we need to substitute dou square V by dou x square. So you just square it. Dou square V by dou x square, that is 4 by LE square, and this square dou square V by dou zeta square. Now you can substitute the value of dou square V by dou x square as 4 by LE square dou square V by dou zeta square. Okay, let us substitute this V value. V is equal to HQ. V is equal to HQ. What is H value? H1, H2, H3, H4, and Q is Q1, Q1, V1, V2, and theta 1, theta 2. Okay, substituting this H1, H2, H3, H4, it is written separately in the matrix form. Dou square H1 by dou zeta square, dou square H2 by dou zeta square. Okay, in this fashion written, because all the Hermann shape functions, it is in terms of zeta. Okay, next, this is the nodal displacement vector. Okay, so dou square V by dou x square, it can be defined as this matrix into nodal displacement vector. Okay, all these constants are this matrix, it is called as the C matrix. Okay, this value it is C. Okay, 4 by LE square and this one. Now let us come to the derivation of stiffness matrix. U is equal to strain energy equal to this values. Substituting sigma and epsilon, we already know that sigma value is E into Y dou square V by dou x square. E into Y dou square V by dou x square. Similarly, epsilon is equal to Y into dou square V by dou x square, A into dx. So dou square V by dou x square, dou square V by dou x square, it is 2 times, so it is square. Y also we have 2 values, so it is y square into a dc. We can say that a into integration of integration of y square into a, it is area moment of inertia. So it is I. Integration of y square into a, it is area moment of inertia. So substituting this value, half of EI, okay, it is constant values for the given material. Integration of dou square V by dou x square whole square into dx. Now what is dou square V by dou x square? We have already seen here. Dou square V by dou x square, it is written in this fashion. Dou square V by dou x square, this is constant, this is C matrix, and this is Q matrix. So this dou square V by dou x square, it is C into Q. Dou square V by dou x square, it is C into Q. Okay, into dx. Okay, dx it is converted into natural coordinate system. Now we have two values of C and Q. One we are taking in terms of transpose and one regular. So it is CT, QT and other CQ. Okay. Now if you eliminate the Q terms, then it will be stiffness matrix. So KE is equal to, so if QT and Q, these are the displacement terms, if it is removed, what you will get, all this expression, it is, that is stiffness matrix. This is the stiffness matrix of the element. Okay. Here if you eliminate QT and Q and half, it will be stiffness matrix. This is the stiffness matrix. Okay, let us substitute all these values to get the stiffness matrix of the beam element. We already know what is C value. C value, it is a constant, this matrix, and CT is transpose of this matrix. What is H1, H2, H3, H4? That are the Hermite shape functions. H1, H2, H3, H4 are the Hermite shape functions. It is derived here. Okay, so you find what is dou square H1 by dou zeta square, dou square H2 by dou zeta square. You find all this value and also the transpose form. Okay, you substituting all these values, you will get this matrix. This is the stiffness matrix of the beam element. Okay, substituting all the values, EI, C it is a matrix, CT is the transpose of this matrix. Okay, you then integrate with respect to zeta. Thank you.